Okay, everybody. So let's see. First, I want to go over a few questions that people asked. Sorry for my voice. I'm feeling fine. It's not COVID. I just have a cold, so I've been testing and all that. So don't get too close to me, but I don't have COVID. Um, I have a few questions that people sent in over email that can't come. I'm going to address those first. Can y'all hear me? Okay. There we go. Can you hear me? Okay. And then I want to go over this exam because this spring 19 exam is a good indicator of what you'll have in the free response. I've already told you what they are, but we'll go back over that, and then I'll open any questions that you might have, okay? So we'll get to that. I have a meeting at 3:30, so I can't go over an hour. I don't know that I'll last more than 45 minutes anyway. So first of all, a student asked about this question, which is a good question. You're going to have questions like this. In fact, I told you on the free response, I'm going to give you this diagram and ask you to trace out the rays. But you also need to be able to tell what are the indices of refraction, how are they related to one another, or the speeds, how are they related to one another based on a diagram that you get like this. So the way that you do this is you imagine a front of waves traveling along. Here, because of the way that it turns, I know that it's traveling slowly here and faster here, because this has to speed up in order for the ray to turn like that. So I have slow and fast. Light travels slower when n is bigger. So I know then that n1 is bigger than n2. Then I go to this next one. My light rays travel here. They're going to have to slow down in this medium and travel faster in this medium because it travels fast and it turns in this way, and the light waves turn in that direction. So that tells me that N3 is bigger than N1. Yeah, N3 is bigger than N1. And then I can look at N1 and N3. We've done this before where I have N1 and N3. And I'm going to draw the rays as they are here and here, where they bend towards the normal, like that. And then I draw my wave fronts. They're going to travel, slower here. Slow, fast, because this thing has to swing around like this, like in a twin propeller boat or a tank, if you're doing a tank. I don't think any of you have. But that means that N3 is bigger than N1. Okay? I'm sorry, I did this. This should be N3 is bigger than N2. Right? That's correct. Yeah, N3 is bigger than N2. So N3 is bigger than N2. It's bigger than N1. So my inequality would look like this. N3 is bigger than N2 is bigger than N1. The way that I wrote these inequalities is not really correct, but I think B was the right answer. Okay? You'll see questions like that where I ask you to compare the indices of refraction or compare the speed of light. So that was one question that we had. That was page 134. Another question came up on page 119. Hold on, I'm not sure which one it was. I think it was this one. I'll look at both of them. This is just in the workbook. We work these in class. So on this one, I want to know what is the magnetic field due to these two wires. This is our third application of the right-hand rule. Let your thumb go in the direction of the current, and then your fingers wrap around. Let's do the one on the right first. So thumb goes in the direction of the current, fingers go into the page on this side and out of the page on this side. And then to do the others, let your thumb go down, goes into the page on this side and out of the page on this side. So at a point A, it's going to be out of the page. Now, if you had the current in the same direction, it could be that you have two wires with a current going up in this direction, up in both directions. So on this side, I'd have it like that and like that. And then on the opposite side, I would have it like that and like that. In which case, at a point equidistant, my magnetic field would be equal to 0. Okay? We can come back to that. We'll see more like that as we go on. And then, I'm not going to go through all this, but you will see, in fact, where I give you multiple wires and I ask you for the direction of the magnetic field. So that would look something like this. Let's say I give you, I don't even know what this is going to give me. Something like this. And I ask for, what is the magnetic field here? Right in the middle, I'll call that point P. Hey, Annie. So I go through. Let's do this one first. I imagine my thumb in the direction of the current. At this point, the magnetic field is going to be in that direction. For this one, the magnetic field will be in that direction. And for this one, it'll be in that direction. And then for this last one, it's going to switch it up because my thumb's going into the page. The magnetic field would be in that direction. So my net magnetic field, if I asked you for the net magnetic field, these two would cancel out and these two would add up. So it'd be a vector in that direction. You will have a question like that, and we can look at some of the other old tests. I'm not going to give you a collection of 12 wires like this, like I said in class, just because that takes too long. But you will have to apply the right-hand rule in this way. Somebody asked about 2018 problem 15. That's exam 3, mostly exam 3s on this exam. So a positive particle travels through a magnetic field. In order for the particle to go undeflected, an electric field must also be present. What must be the direction of that electric field? And this student asked me to do it instead with a positive particle, to do it with a negative particle. Okay, so we're going to do it a little bit differently here. First thing I want to do is figure out what is the direction of the electric force or the magnetic force. So I let my finger go in the direction of V. Magnetic field is into the page. Magnetic field is into the page. That means that the force would be up if this was a positive particle. But it's not. It's a negative particle. So the magnetic force is down. That means to go undeflected, the electric force must be up. Okay? Which means that the electric field must be down. Because a positive particle feels of electric force in the same direction as the electric field. When it's an electron, it's like everything gets switched around. So since my electric force is up, my electric field is down. Okay? You could see a problem like that where I have competing magnetic and electric fields. And then a student asked about the fish in water problems. Yeah, Luis?
Can we do number 10 for this one afterwards?
Yeah, let me address these things first. Okay, well, this one right here, and then we'll come back to it. Can you ask that? I want to address these questions that students sent in, and then I want to address the free response. Then we'll come back to it, okay? Okay. Do you have a fish in water? So here's my fish, my water level. Now, if you're over here and you're seeing this fish, if there was no refraction, you would just have a light ray. That would just travel from the fish straight to you. And then you would see the fish actually where it is. But that's not what happens. Actually, you get a light ray that will come out, and then it bends away from the normal because I'm going from a high to a low index. Is that right? Yeah. So it speeds up and it goes towards your eye like that. That's actually what happens. Then to figure out where the image of this fish is, you're going to trace this ray back, the refracted ray, and you'll find that your fish is there. Or you could say that the fish is there, either above or to the right of there. Okay? Now, if you're looking from the other direction, it'll be above or to the left of the fish. So don't try to memorize the situation. Instead, think about how I draw the rays for this refracted light. Okay, we can look at some multiple choice questions like that in a bit. Now I want to go over the free response. You're going to have 4 parts to your free response. One is going to be an RC circuit, and you're going to have to solve for T. I'm going to ask for what is T. I'll have 2 questions for each of these 4 questions, so they'll add up to 8. So the first is about an RC circuit. I'll ask, what is the time to get the whatever charge? It's just like spring 19, that problem number 1. We'll work that in a second. And then I'll ask another question. How long does it take to fully charge or discharge? What is the time constant? That sort of thing. The second problem that I'll ask is mass spectrometer. The third problem that I'll ask is well, I'll show you an example of what that means. The third problem is a magnetic field due to a wire. And then what is the force on a particle? A 2-part problem. I'll show you that example. And the fourth thing that you'll see is a refraction problem. I've already told you this. I'm going to give you a figure that looks like this with the indices of refraction N1, N2, and N3. I'll tell you the initial angle. So I'll tell you this is 30 degrees or whatever it is. And I want you to tell me, I want to know what is this angle. Okay, what is that angle in that third medium? Okay, I'll work that problem. In addition, I want you to draw the rays. And I'll be looking to see that you get the proper perspective. Are you moving towards the normal or away from the normal? Please exaggerate that as much as possible. I tried to make the figure as big as I could. All right, let's look at spring 19. I haven't forgotten your question. We'll come back to it. But let's look at spring 19. Because it's a good example of the free response. In fact, this number 1 is just like you're going to see, except with different numbers, of course. But otherwise, it's exactly the same. So y'all practice this tonight. Make sure that you can do it without even really thinking, that you don't have to really think about it at all, that you can do it in just a couple minutes, okay? So here, I want to know at what time is the charge on the capacitor 5 microfarads. You can look on my equation sheet, but you shouldn't have to look on your equation sheet because you know this question cold by tomorrow. And you'll find that the charge is 1 minus e to the minus t over RC. Let me fix my pen here. Okay. And I want to solve for t. So Q is 5 that should be microcoulombs, 5 microcoulombs. I'm going to keep the micro. We'll see that the micro cancels out. Big Q is the charge on this capacitor when it's fully charged by this battery. So it's equal to C times V. That's going to be 18. 3 times 6 is 18 microcoulombs. So 5 is equal to 18 times 1 minus e to the minus t divided by RC. Tau is equal to RC. That's equal to 3 times 2, or 6 seconds. Notice the micro and the mega. I don't have to account for those because they cancel one another out. Mega is 10 to the 6, micro is 10 to the minus 6. That's the way it'll be on your test tomorrow, okay? That's common in RC circuits because you're often want a time constant that's on the order of seconds. So that's t divided by 6. And now the hard part of this is, or it's not hard, but the thing you need to do is now solve this for t. The first thing that you'll do is divide through by 18. That cancels out the 18. And then I get 5 divided by 18. I'm just going to put in the numbers. I know y'all usually do that. So it's 0.28. You can solve this algebraically first, and that's always better, but I know y'all usually put in the number, so I'll do it that way. 1 minus e to the minus t over 6. Then you want to subtract 1 from both sides. So that's, these ones cancel, and I'm left with negative 0.72 is equal to e to the minus t over 6. Then I take the natural log of both sides. Natural log of this side, natural log of that side. That gets rid of that e. And the natural log of negative 0.72 oh, it should be positive 0.72 because this is negative, so that goes to negative. Is that right? No, 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 no. Oh yeah, I'm adding 1 too. I don't know. What are we doing? I'm subtracting 1 from both sides. Yeah, I missed a negative here. Sorry, y'all, I'm not quite all here. So I have a, if this is negative 0.72 is equal to e to the minus t divided by 6. So yeah, so I'm taking the natural log of positive 0.72, which is negative 0.33, and that's equal to negative t over 6. And so t is equal to 6 times 0.33, which is 2 seconds, basically. Okay? The way that I've done this to give you more space is I've put the first problem on the bubble form. So you know you have that bubble form and you have that block that I say you can write in. That's where problem number 1 is. That's this problem. And then the other 3 problems I'll put on the back side of that paper. So that's what you'll expect to see. Okay? And then I might ask you part B, part C, one of those. Remember, to fully charge a capacitor is this value times 10. So for this one, it would be 6 times 10 or 60 seconds. I could ask you to graph this. This is a growth function, so it's going to look like this. You need to know those anyway. We'll look at those. The answer is either going to be that or that, a growth or decay function. So you'll have a multiple choice about this. Okay? That's one question. The other question is just like number 2, in fact, except I'm going to ask you to draw the rays. Here I asked you to describe it. Louis?
Will we be given all our indices of refraction?
Yeah, I'm going to give them to you. So I'll give you those indices of refraction, and then you have to draw them. So here I'm moving from a small to big index, so it's slowing down. That means it's going to bend towards the normal. And then it goes to another bigger index, so it's going to bend towards the normal again. Try to exaggerate this as much as possible so that I can see. So if it bends away from the normal, make it go really far away from the normal. Okay? If you think it's not clear in the drawing, you can just say away or towards on the diagram, just so that it's clear to me. And then I'm also going to ask for what is this angle right here. All right, I tried to describe it in words as best I can, but I'll explain it to you in the class tomorrow too, just so it's clear. I think I described it as the angle after it emerges into the third medium or something like that. But I'll draw a diagram tomorrow and tell you what I mean. I want to know that angle in order, just like I say here, as it enters the third medium. To find that angle, I say N1 sine theta 1 is equal to N3 sine theta 3. So that's going to be 1.1 sine of 50 is equal to 1.5 sine of theta 3. And then you solve that. You have to take the inverse sine of 1.1 sine 50 divided by 1.5. and then that'll equal your angle. Make sure that you're in degree mode. I've encountered several students lately that have been in radian mode, so just be careful. I probably had 3 to 5 students. I don't know if y'all are in calculus right now, but sometimes in calculus you have to put your calculator in radian mode, but never, at least not in this semester of the class. That's problem number 2.
It has to be in degree form?
Degree mode, yeah. So you go to mode, usually second, mode, second, or mode, and then click degree. All right. And then you're going to have one like this with a mass spectrometer. I might ask you what is the radius, or I might ask you the mass to charge ratio for that. Any one of those is going to be R is equal to mv over qb. That's your cyclotron equation. If I'm asking you to calculate R, you'll just be using those values. If I'm asking you to calculate the mass to charge ratio like we've done in class, it's going to be RB over V. Okay? I might also ask you for the direction of the force or the magnetic field. Like in this one, I asked for the direction of the magnetic field. So a very similar question to this one. The direction of the magnetic field I can find because my velocity vector is in that direction and my force is in that direction. Double check that is a positive particle. Index finger in the direction of the velocity. The force is my thumb. So that means my magnetic field is out of the page. My magnetic field is out of the page. Okay? There are 3 or I think 3 explicitly right-hand rule questions, but it comes up in other questions too. So make sure you have your right-hand rule down pat, that you know it really well, because it probably works into 6 to 8 questions, which is a lot for the exam. But there are 3 explicitly right-hand rule questions. All right, the 4th question we've done before, but there's not an example here, is going to be, I'll give you a wire, I'll give you some current, I don't know, 2 amps or whatever, I don't know what it is, and then I'll say, what is the magnetic field over here? You can calculate that magnetic field, mu naught I over 2 pi r. That's on your equation sheet. R is just the distance from here. Let's say that this is 3 meters. I would calculate that. Let's make it 4 meters, just make the math easier. I'll calculate it by saying 4 pi times 10 to the minus 7. 2 amps divided by 2 pi times r, which is 4 meters. And I get some cancellations here. Boom, 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 boom. So I get 3 times 10 to the minus 7 Tesla. So that is my magnetic field. And then I will also ask a second question. Hey, what if you have a charge right here moving with a certain velocity? Let's say that that velocity is 6 meters per second or whatever. And I want to know what is the force that that particle feels. If Q, I would give it to you. Let's say that that would be 4 coulombs. I would say F is equal to QVB sine theta. Theta is not relevant there because it's sine of 90, which is 1. Just a second. And so that's going to be 4 coulombs, 6 meters per second. B, I find, is 3 times 10 to the minus 7 Tesla. So that's 24 times 3, 60, 72 times 10 to the minus 7 newtons. That's the 4th question with 2 separate parts. Please.
Would you say if it's a proton or an electron?
I could say that, yes. So if I don't give you a charge or a mass, in fact, I know for a fact that at least in one question I don't do that, but I've told you in the text that it is either an electron or a proton, in which case you know both the mass and the charge. Let me show you in the equation sheet. So on the equation sheet, the mass of an electron or a proton is right here. That's the fundamental unit of charge. Excuse me, not the mass. The charge is right there. It's negative if it's an electron. And then there are the mass of the electrons and protons. I do give you the entire equation sheet for this test, so just beware that's what you're going to get. Unfortunately, The equation sheet is on the back page of the exam. I was just trying to save some paper. Love y'all, but yeah, no, you're worth 85 pages of paper. But I thought if you wanted me to save 85 sheets of paper, that's better, right? Yeah, you are worth a lot more than 85 sheets of paper, but you're smiling, right? Are you smiling? Yes. Bye. Okay. So anyway, you're gonna have this on your exam. Okay. Return back to that's the free response. 100% on that. Okay, y'all. You know exactly what it's gonna be. 100%. I want to see big dark lines on your exam. You know that the big like a good exam is when they got a big dark line all the way down through all the little circles on the far off sheets only. That's what I want in everybody's exam. Because you know exactly what's on there, and I want you to get those perfectly and quickly, all right, so that you have lots of time on the rest of it. Y'all can do that for me? It'll make my day. I'd be so happy if that happened. Just say, yeah, you'll do it? Okay, good, 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 good. Let's look at what was that? Was it this one? This one, number 10, is that right? Please?
Yes, sir.
Yeah. So an electron. Okay, so this could be like your free response, but you will also see a mass spectrometer question in the multiple choice part. I try to keep the math, your free response, there's a lot of math that you have to do in the free response. So I try to keep the math at a minimum, but you will see some. Here, let's just figure out the force. F is QVB. Sine theta. Don't forget your sine theta term, though, and often the angle's not given. That means that it's orthogonal or perpendicular, which it is. It's x and z directions. Those are orthogonal to one another. Negative or 1.6 times 10 to the minus 19. It's an electron. I'm going to circle this so I come back and I think about it at the end. V is 3 times 10 to the 5th. B is 0.8 Tesla. And that gives me my magnetic force. Which is 3.8 or 4 times 10 to the minus 14 newtons. But look, I got a couple of those, so I need to figure out which one it is. So my velocity is in the positive x direction, and then my magnetic field is in the positive z direction. Now I can figure out the force. V is out of the page. That means my force would be down, except this is a negative particle, so my force is in the positive y direction, or upward direction. Okay? That's more like your free response, but you'll see questions like that too in the multiple choice. All right, what else, y'all? So that's the end of people's specific questions and the free response. Yes, Lex. Sure. No. Okay. Is that okay? Can we just leave it at that? Okay. What else? Logan? Huh?
Some solenoid questions.
All right, Logan had his hand up. So what's up, Logan? Is that exam 3? Right. Okay, yeah. So a lot of people have been asking about these. What's important here is that the force due to our electric field has to equal the force due to our magnetic field. Now, if you've forgotten the equation, it's on the equation sheet, but it's under chapter 2. But that electric force is QE, and the magnetic force is QVB, sine theta. But there is no sine here, so no theta, so I'm going to leave it out. The Q's are going to cancel. So they're both electrons, but they cancel out. And then I'm looking for the velocity, which is going to be E divided by B. E, I'm told, is 2,000. B is divided by is 0.8. So 2,000 divided by 0.8 is 2,500. So that would be the answer there, 2,500. Now, you don't have to do anything with the right-hand rule in this, but I mean, this one is relatively simple. But if you're thinking about the right-hand rule, let's say that I didn't know the direction of the electric field. Can we do that? Can we imagine that problem? So let's say that I know the direction of the magnetic field is in this direction, and I asked you what is, like I could say, no, let's do a different thing. No, never mind. Let's say, what is the direction of this velocity? I don't ask that in this problem, but I could have. Yeah, let's ask what is the direction of this velocity. So this is an electron. That's really important. In fact, if you ever see an electron, make a big star on your problem to remember that as you go through the problem. It's an electron. That means that the electric force is going to be opposite the electric field. Fe is opposite the electric field. That means that the magnetic force has to be in that direction. So now I'm going to redraw this. There's my magnetic force, Fb. There's my magnetic field, B. And now I can ask, what is the direction of the velocity for a particle traveling through this magnetic field to get this force? B is your middle finger. Oh gosh, this is hard. B is your middle. B is your middle finger. Oh, looks like that. Okay, that means that the velocity would be into the page, except this is a negative particle, so it's out of the page. So if this were a positive particle, the velocity would be into the page. Let me just double check that. Velocity's into the page. No, that's not right. It would be out of the page, right? You got that? Out of the page? Yes. I can't get rid of that. I'm sorry. So B, FB. If it were positive, the velocity would be out of the page. But it's not positive, so that means it's going to be into the page. Okay? That's probably what you were really asking, right? Yeah. Because this problem, if you know how to do it, is not difficult. Of course, that's true for everything. If you know how to do it, it's not difficult. But this part with the right-hand rule, it gets a little detailed. So, especially if the particle is negative. Chloe, are you raising your hand? Are you thinking?
So if it's an electron, the velocity doesn't switch. Obviously.
Right. So if it's, can you repeat that?
So the electron, the fact that it's negative doesn't affect the direction of the velocity. It's going into the page or out.
Okay. Let me just repeat. Can I clear everything here? So I know that was unclear. My magnetic field is in this direction, and my force was in this direction. That's right, right? Yeah, the force was down. So magnetic field. This is where it's useful to shift your paper around. So your velocity would be coming out of the page if it were positive, but because it's negative, it's going to be going into the page. Everything shifts. If it's negative, anything that you're looking for is going to be opposite of what you're looking for. That answers your question, right? Okay, yeah. Sorry, that wasn't really clear. I'm sorry. Okay. What else, y'all? Yeah, Tyler. On this one? Well, at least I haven't forgotten you. We'll get to you in a second. Okay. So this is like your free response. You're going to have one like this on your free response. Except there'll be calculations involved with that one. Positive particle, that's good. Makes it a little easier. I have a velocity in this direction, right? It's initially traveling down, but it has a force that's moving it to the right. So my velocity is down, my force is to the right. That means that my magnetic field, if I'm doing this right, is into the page. Velocity is down. Yeah, my magnetic field is into the page. So a current that will produce a magnetic field in that direction is a current that is moving from right to left. I let my thumb go in the direction of the current. On the top of the wire, my fingers go into the page. On the bottom of the wire, they come out of the page. That's right. Using your pen is a really useful thing, especially for this one. So think about that. Okay? You'll have to do that on the free response. Think about the direction of the current or magnetic field or whatever, but also maybe in the multiple choice. As usual, there are 20 questions on the multiple choice. Okay, and you were asking about solenoids. So this is a good example of a solenoid. There are two types of solenoid questions that you can have. I could give you a coil of wire and ask you what is the magnetic field inside of that coil of wire. And then that's a simple calculation. It's mu naught I over 2R, and you're multiplying it times N. So you look at the number of turns of wire, you get your mu naught, you get your current, you get your radius of that coil, this distance, and then you can calculate the magnetic field. Probably you're asking about this right-hand rule, and this one tends to be a little more difficult. So I pick a strand. I'm going to pick this strand, and that current is up. So imagine my thumb going in the direction of this current right here. My fingers behind the wire are to the left. In front of the wire are to the right. So inside of this coil of wire, I'm going to have a magnetic field that's to the left. Imagine this is my wire. This is the little section of wire right here with the current going up. Behind that wire is going to the left. In front of the wire, the magnetic field is going to the right. So inside of that coil, which for a solenoid is really all I'm worried about, inside of the coil, the magnetic field is to the left. So A would be the right answer. Okay? All right, what other questions we got? I can sort of scroll through this. Don't forget your light stuff. You're going to have electromagnetic spectrum. You're going to have the nature of light. You're going to have refraction. You're going to have a question like this. I told you all this. Don't be surprised by that. Stuff like what is the speed of light through different media. Students tend to be better with those. That tends to be the easier chapter. But, you know, if you haven't reviewed it, it's not going to be easy. Logan? When would what not occur?
We have two real things happening on the test for all that, but actually, like, you have examples like some of the light stuff where it always says it's this video, another video, and at the end it says.
Oh yeah, okay, I know what you're talking about. Total and thermal reflection. That's what you're talking about, yeah. Okay. So you will have a total internal reflection. I think 2 problems on total internal reflection. 1 or 2. Probably 2. When I have a material, and let's say this is n equal 1.5 and n equal 1. If I have a light ray that enters, or it comes to that interface at a particular angle, and that angle is the critical angle, it's going to, if it's at the critical angle, the refracted angle is going to be 90 degrees. That's theta 2. Total internal reflection does not occur if, for example, I have an interface where this is n equal 1 and this is 1.5. In this case, I have a light ray that comes up, but instead of bending towards the normal, or excuse me, away from the normal, it bends towards the normal. So this will not have total internal reflection because I'm moving from a small index to a high index. Now, if I'm asking you to calculate theta critical in a situation like this, if you don't recognize that, hey, I'm moving from low to high, then your calculator is going to give you an error. It can't do that inverse sine. It just doesn't exist. So that'll be a key. If that happens, just go, whoa, what's going on? Do I have this situation? Don't just switch the order of the indices because that might mean that that is the answer in fact. Okay, does that answer your question?
So it would only be in a situation like that where like one at the top.
Yeah, only when I'm moving from low to high index of refraction, because in those situations my light is moving towards the normal, but really to have total internal reflection it has to move away from the normal, and the critical angle has to be just right too. I mean, it is possible for this light ray to come out and not actually get reflected back in, but that's the critical angle. That's how we calculate. Okay, all right, I'll just sort of skim through here. If you get to things that start talking about images or atmospheric refraction, that's where you stop. The spring 19, oh, this is spring 16. The spring 19 exam is a really good one. Not that I've used those questions, like I've written new questions, but it's just, if you haven't worked that one yet, I would this evening sit down and just work it all by yourself without any help and see how you do on it. If you do well on it, then you should be ready for tomorrow. Okay? Okay, Chloe?
When we have to draw like tangent lines for magnetic fields, how do you, like some of them, when we're drawing them like as extensions from others, how do you know you have to do that? Like sometimes they cancel out, but other times they're just like in the same position as the other one.
Yeah, so I think you're talking about where if I have multiple wires like this, right? Like that. You are going to see this. Let's just go through it, okay? So this is my, I'll call this black wire, this blue wire. I'll draw them red. I'll draw this one black. Okay, so let's start with this wire right here. My magnetic field goes around and in this direction. And so at any point, the magnetic field is tangent to that circle. But over here is tangent in that direction. So if I imagine my magnetic field at this point, it's going to be in that direction. You follow me? I'm drawing it tangent to the circle. And then in a similar way, it's going to look like that. Because right here it's there. And if I just translate that over in the center of the square, it's going to be in that direction, tangent to the circle. And then right here, it's going to look like that. That's the red wire. And then for that last black wire, it goes around like that. So over here, it's tangent to that direction. Now, all of these, none of these cancel out another out. So they're going to have a net vector that's like that. If I had vectors where I had one like this and one like this, those two would cancel one another out. They're both operating at this point in space, but they're equal and opposite, so they cancel out. I think that answered your question. Am I right? Okay. That's good. You're going to have a question, or maybe two, like that, where you have to use those skills. And y'all got some mad skills, right? And show me those mad skills tomorrow. Is that a phrase that people still use? I think it's from like Napoleon Dynamite or something, I think. Is that what it's from? He's got skills? You haven't seen that movie, have you? You have seen it? Okay. All right. What else, y'all? Just skimming. Let me holler out if you see something. Make sure you know your stuff about basics of magnets, poles of the earth, yada yada, all that. Yeah.
Number 5, we transform centimeters to meters.
Of course, yes. So, if ever in doubt, transform centimeters to meters. In fact, I don't think there's a situation where you don't need to do that. There's not in this chapter. It's really just dealing with the RC circuits that you can keep the micro and the mega and all that for the free response. But you're not going to go wrong converting it to SI units. You never go wrong converting to SI units. Alrighty?
Did you say that we were going to have one on 2016, number 19?
Is that the percent one?
No, that was the fiber optics people.
Oh, sure. Yeah. Yeah, that you need to know that this index right here, that this index is the low index, and that this index is the high index. That the index of refraction on the inside is always bigger than the index of refraction on the outside. Like, think of a fiber optic cable. It's glass or plastic surrounded by air, right? It's always higher in the middle than it is on the outside. So yes, absolutely. Very similar question to that, Fanny. Okay? No surprises tomorrow. I want everybody to know right up front what I expect you to know, okay? But it's not easy material, so you need to practice, practice, practice. Okay, okay? All right, y'all, guys.